Hello folks, this is Todd Coburn of Cal Poly Pomona with lecture 13 of Aero 3271. Today we're going to be continuing our study into fasteners, and we're going to be looking specifically at tension and fatigue of preloaded joints. We talked about preloaded tension joints last time. We're going to be talking about fatigue this time. So let's first take a quick look at what we learned last time. We learned about the equivalent bolt stiffness, how to calculate that. Usually we're going to have two terms, one for the shank, one for the threads. We learned how to calculate the member stiffness. We learned that we were going to take a cone at 45 degrees. Now we recognize that other cone angles can be used like 30 degrees, even 60 degrees, but we're going to use a cone of 45 degrees in this class, which keeps our analysis simple and straightforward. We introduced the joint stiffness constant and learned how to determine what the joint forces are in the bolt and the clamp up forces in the members. Now these two equations once again are valid as long as the members remain in compression, as long as the force in the members is negative. If it's zero or positive, then actually that's incorrect. It's not possible. That means that it's unloaded, that your joint constant is ineffective, and all the load goes into the bolts. Now when we want to do fatigue analysis, having recognized everything we just learned in the last lecture, we saw before that with fatigue we had to characterize our loading. We had to look at the loading parameters, which basically involved identifying the max and the min load so that we could identify the mean and the alternating stress and calculate the fatigue on that basis. We're going to do a very similar thing with some slight deviations for bolts. The bolt load, we'll look again at the max and the min bolt load. We need to get that first. First, we're going to take our spring constant. We're going to use this equation as long as, once again, the members remain in compression. If the members remain in compression, then our constant C is whatever value it is. If our members are not in compression, if there is zero or positive, then C is 1 and all the load goes into the bolt. So we identify the max and min bolt loads. We then calculate the mean and alternating bolt loads. Well, that's just, or bolt stresses, excuse me. That means we just need the max stress and the min stress to calculate using these equations. Since the stress is just P over A, we can write that equation in these formats here and come up with a value for the alternating stress, either using just calculate the stress max minus min over 2, or use this final equation where the alternating stress is the joint constant C times P max minus P min over 2 area tension. In the same way, we can calculate the mean stress. So these two equations can be used to calculate our stresses in the bolts. Remember, C is just calculated from the formula we got before as long as the joint remains in compression, the members remain in compression. Then what we're going to do is go and look at, for that bolt, what's the stress concentration factor? Well, we're going to look at that next slide, but we're going to find out that really the only thing for the bolt, we have a stress concentration factor at the head, another one at the thread, but we're going to bury that in the endurance limit for the bolt rather than FM or FE or FA. So this is a different approach, slightly different path that we're going to take to fatigue than we learned when we calculated fatigue before for general parts, and that's because our stress concentration factor for bolts themselves are already accounted for in the endurance limit, which means we're not going to apply it to the stresses themselves. Okay? Now, if we actually looked at a bolt, we would find that 15% of those failures occur underneath the head of the bolt, 20% underneath the thread, and 65% at the thread at the nut face. Let's go ahead and take a look at that real quick. Let's go ahead and draw a bolt here, and let's assume that this bolt is clamping together some parts. So we have a fillet here, there, and then we go into our threads, and then we have the end of the bolt. And down here we have some kind of nut. So we're not even going to draw the washer. Whether or not there's a washer is irrelevant to what we're doing here. So we're going to see, okay, 15% occurs underneath the head. That's right here. 15% of failures. Remember, if we are pulling tension on this bolt, which is pulling the joint apart, what's going to happen is the head is sitting in a material and it's flexing like this as the shaft of the bolt is being pulled downward, that causes that head to flex. So since that head itself is in bending, we've got tension on this shank, right? P over A on the shank, P over AT, right? And we're going to get, because of this fillet here, we're going to get a little stress concentration factor. Now that's why we don't make a really sharp fillet here or a really sharp transition from the bolt to the head. We tend to have a nice rounded joint. Now for all of our bolts that are made to like SAE or ST or ASME standards, there's a requirement for what this radius should be underneath the head. So these made to a standard will all be accounted for in the same way. And that's designed to not have too big of stress concentration factor. Because we're getting flexing of the head that's pulling up in that radius right here, that's going to tend to cause failure where we can get something propagating through the bolt. About 15% of failures occur there. Okay? Now, about 20% occur at the end of the thread. If we take a look at this, you know what, I'm going to redraw this really quick because I don't like, or actually let me see if I can erase part of this, like, oh, there we go, that works. Let's just erase my nut and I will redraw that nut for you guys so you can understand this better. Typically what's going to happen is we're going to have parts that are attached together like this, right, and with some split line. And then we're going to have a nut on this puppy. And you'll notice that the start of the threads is right here, and then the start of the nut is down here, okay? So 15% of the failures occur here underneath the head. 20% of failures occur here at the first thread. What happens is we have a certain shank diameter, and that's the area of that is the area of the shank, which we used this nomenclature, either of those. And then, I'm not circling this equation, I'm drawing that cross section. And then what happens is on that circular cross section, we've got a thread cutting through it. So what happens is we go from the area of the shank to the tension stress area, A sub T, and there's a little cut out of that area which introduces some stress. That's the first place it happens, and so we're going to tend to get about 20% of the failures there. Okay, now if you look at so basically once you hit that, you're going to continue. Each thread is going to have a similar stress concentration factor. That first one will probably be the worst, but then we get to the nut. Now where the nut is interlocked with the thread, let's say the thread's like this and the nut locks in here. Wherever the nut is, remember that's where this loading is, and that's going to tend to stretch the one thread, the first thread at the nut face. The first thread after the nut face is going to tend to open up. That's this one down here. And because that one is got the same stress riser nearly as this, but then it also has that thread, see how that thread is flexing? It's causing flexing of the thread in addition to that tension. That's going to end up making this worse. So about 65% of failures are going to occur right there at the first thread after the nut face starts. So that's where these failures occur. Now we're not going to do anything with that other than to recognize that that is where we would expect failures to occur. For this reason, this is why we have a nice healthy radius underneath the head of the bolt, and this is why we tend to like to use rolled threads, which give better fatigue properties rather than cut threads. All right. Now, once again with bolts, we're going to have to choose a failure criterion in the same way that we did before. And the difference now is that, remember before, what we would do is when we looked at fatigue before, once we chose a failure criterion, we would go out here and plot the mean stress of our point against the alternating stress. That gave us a point. And then we draw a line from the origin through the point and look at the relative differences, relative dimensions of proximity to the failure line in order to evaluate the margin of safety. Now we're going to do the same basic approach, but instead of starting here at 0, remember the bolt, if it's preloaded, it has a stress to start with. So the mean stress starts at that preload here. Whatever the preload is, that's the preload stress. And then we plot our point mean versus the alternating. And once we've done that, we draw a line from that preload through that point like this. Now, we're actually not going to have to do this because we've got a closed form equation. I've already given you that equation here. This is the equation of the failure line from where it's preloaded to whatever point. So we just plug in our preload stress, we plug in our mean stress, and our alternating stress, along with the FTU of the bolt, the S sub E of the bolt, and that gives us magically, you say abracadabra when you plug in your numbers, and out pops the margin of safety. New math. Okay. Now for yield, remember, we might also want to check yield. Remember, if the stress is too high, the bolt might yield, and if the bolt yields, you may see a change in the properties based on what we calculated originally. So this is kind of like what we call the Langer criteria. We're basically taking the max stress and evaluating against yield. Now for bolts, rather than checking yield, now if you have an aerospace bolt and you don't have the proof or proportional limit of the bolt, the proof load of the bolt, the proof stress, then we will use the yield allowable. But many of our non-aerospace bolts, what we had was an FTU, an FTY, and a proof load, or proof stress, and in that case, we will use the proof allowable, which we're calling S sub P. That's the proof allowable. So if you go to a non-aerospace bolt, you look at that column that we introduced a couple lectures ago, that will give you the proof load. If you don't have a proof load because it's one of the materials that's like in the back of your handbook rather than one of the bolt materials that we gave you, then we'll just use S sub Y there, okay? The FTY. You got your thread area and your max loading. You can find out if there's yielding. Now, if there's yielding, that doesn't mean you have a fatigue failure. It means you might have one. It means that the margin of safety fatigue might not be valid, okay? Now, the other thing we need to do is check for separation. We need to make sure that the joint doesn't separate, or more precisely, that the members that are being squeezed by the preload of the bolt don't unsqueeze under those loading. If it unsqueezes, that means our C becomes 1 and all the load goes into the bolt. So the way we're going to do this is not take the member load that I gave you an equation before. We're going to take part of it. We're going to take the member relaxation due to the external load, which basically is this equation here. You're going to take the preload, and just force is fine, divided by the max external load times 1 minus C. And if that gives you the margin of safety. Of course, this is only valid if your joint remains in compression, and this margin of safety would tell you whether you separate, okay? If we chose a different criterion, like the Gerber criterion, you've got this equation, which has the alternating stress, the endurance limit of the bolt, the FTU of the bolt. You'll notice in the Goodman criteria, I am using SUT, that's just FTU. And in the Gerber criteria, I'm using FTU, which is actually the same thing as SUT, right? So it's the FTU of the material, or the max ultimate strength. We've got the endurance limit, we've got the preload, and we've got and that's it, okay? If we use the ASME elliptic criteria, then we've got this equation. We're going to plug in the endurance limit, the alternating stress, the proportional limit of the bolt. Notice this is the proportional limit of the bolt. If we have a bolt that we don't have a proportional limit from that table, then we'll use FTY. But if we have a proportional limit listed in the, like for non-aerospace bolt, then that's what we'll use, okay? That's how that works. Now, I told you we weren't going to apply a stress concentration factor. This is the the fatigue stress concentration factors for different grades of bolts. The first column is for rolled threads. The second column is for cut threads. You can see cut threads have a higher stress concentration factor. We also have a value for the fillet underneath the head of the bolt. However, we ain't going to use this because what we're going to do, like I said, is we're going to dump that right into the endurance limit. If we use these endurance limits for 7, 8, blah, 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 then these endurance limits are based on testing, which means that bolts made to those standards already had whatever stress concentration factor was there that was valid. Therefore, these endurance limit include that. So we're not going to apply that. We're not going to apply that fatigue and stress concentration factor a second time. Does that make sense? Okay. So here's a basic, simple, stepwise system. we're going to evaluate our bolt stiffness, K. We're then going to evaluate our member stiffness using that 45-degree cone angle. We're going to make sure we have all the detailed information we need. We're going to compute our effective areas. We're going to calculate the stiffness of each of those. We're going to determine our effective stiffness for the bolt and for the members. We're going to calculate any preload values and any external load values. We're going to calculate whether the joint remains, the members remain in compression or not. We're then going to calculate our max and our min bolt load, and then the average and alternating stress in the bolt. And then once we choose a failure criterion, we will calculate the margin of safety in the bolt. Now remember, when we evaluated fatigue, we were evaluating the margin of safety for infinite life. And if it succeeded in passing that, if it was a positive margin of safety, we expected infinite life. If it was a negative margin of safety, we did an additional analysis to figure out, well, how many cycles is it good for? Now, we could do that for bolts, but we ain't going to do it for bolts. Basically, because bolts tend to have lots and lots of loading on, a lot of cycles. We're going to basically design bolts for infinite life, which means if it doesn't show infinite life, we're going to redesign that joint in this class. Got it? Okay. Here's a little example, this little MATLAB program I wrote to illustrate how this thing works. These are some of the input parameters, and this is the factors of safety for those different failure criterion and such. This actually uses a slightly different approach, which applies the stress concentration factor. But basically what happens is, this is our design point, this little red point here. We see that the Goodman criteria, the modified Goodman is this green line here, blue is the Goodman criteria, and if we plot our design point, we find out we have a healthy margin or factor of safety, because where I plot our mean and our alternating component of stresses here, and we find that it's well within the curve. But what happens if instead of the design point that we have, which had both preload and external load, what if we had zero preload? If we had zero preload, then that means that all of the external load causes stress on the bolt. And what that means is we start out here at this point up here at something like 1 and 3.3 or something. We have a negative margin, and as we start, if we add preload from that 0 point, that means we're talking about right here, right? If we have no preload, then this is our point, and that means if we draw a failure line, we see that we're very negative, okay? Now, if we start increasing the preload, let me get rid of that stuff. If we start increasing the preload, as we increase the preload, our margin of safety, or our movement of that point, gets more and more negative. We're getting more and more negative as we move this way, until some point where suddenly now as we increase the preload, all we're doing is increasing the mean stress, right? We're not changing the alternating stress. As soon as we get to a point that our joint remains in compression, we go from a negative margin of safety here to a very positive margin of safety down here. If we then increase the preload, we start moving this way through our design point and onward until eventually we fail that bolt. So you might think you want to design for this point right here, right? Because that would be the point with where you're not closest. But what happens is you'll notice at this point here, if you have any slight, remember our values were based on the K of the bolt and the K of the members, and the methods we used to calculate these were rather approximate. So actually there's a lot of uncertainty here, and so we don't want to design for this point. What we want to do is design for something that's out here, so any slight fluctuation in our analysis doesn't change that it's a positive margin, but there's no need to increase the preload so high that that same uncertainty could cause us to go outside the envelope. So designing so that we're past this point and then some out in this range here is just a wise kind of idea. Does that make sense? All right, so that's how this thing kind of works. If we saw that on a different, this is Here's my little graphic. Let me show it again. So we're moving from this preload point where we have no preload to more preload till we're finally got enough to stay in compression, and then we just start increasing to our design point and beyond. This is another picture of the factor of safety. We had a nice negative. We had a factor of safety that was less than 1, which means our margin of safety is negative. It gets worse and worse until we get to the point where we stay clamped up. Then our factor of safety and margin of safety both jump up, and then it starts to degrade. That's how that looks. Make sense? So this little chart is just to kind of give you some ideas about design. We're not really going to use this much in our class, but it's just giving you some ideas for what to think about if you're actually designing structural joints. Okay? So you can study this at your leisure and use that as you need to in your project work. Here's a couple conceptual questions. How do we evaluate infinite life for bolted joints? Think about that for a moment. Are we going to do this, right? We're going to select our failure criteria and then use our margin of safety equation. How do we determine non-infinite life? We'd have to go back to what we learned for parts. We're actually not going to do that in this class. Will we evaluate non-infinite life of bolted joints in this class? No, we just said that. Why? Because. What is the difference about our infinite life margin of safety calculations? It looked like I can't spell calculations. Just imagine that C and that U are reversed in that statement. What is different about our infinite life margin of safety calculations for bolted joints versus regular joints? Right? Remember that? Do we use Marin factors? Ooh, there's another typo. For bolted joint endurance limits in this class. No, because remember, everything's included in our SB from testing. Could we? Of course. Should. That means yes. Okay, where do we get the endurance limits for our bolted joints? Actually, these page numbers listed here and this figure number might have changed since I wrote this slide. Okay? So that's all I got for you. This is how it works. You now are armed and dangerous. You know how to calculate, how to get data about bolts, both non and aerospace bolts and fasteners. You know about how to calculate margins of safety. You know how to analyze preloaded joints, joints loaded in shear where the loads don't go through the centroid of the fastener pattern. And you know how to evaluate fatigue of bolted joints. Enjoy.